All right. I think it's 10 a.m. Calgary time, so it's the right time to start. Thank you, everyone, for joining in. Good morning or afternoon, depending on where you are, and welcome to the third webinar series for our Future of Geotechnical Education at the university level. Those who couldn't attend our first and second webinar, our first webinar was Animating Soil Models, Animations as Teaching and Learning Material for Soil Constitutive Modeling. And our second webinar was Embracing Uncertainty, Lessons from My Journey from Graduate Research to Entrepreneurship. And both recordings are now available on YouTube, so I recommend you to check those out if you weren't able to attend. And those who are joining us today, thank you so much for your time, and we are so excited to have so many people interested in this series. We hope that we'll get your amazing support for the upcoming webinars as well. Before we start, I just wanted to let you know that this event is being recorded, and so please bear with us if there is any technical difficulty that we face as we go along. So my name is Shama Roy, and I'm the Vice Chair of the Canadian Geotechnical Society Education Committee. The mandate of the Education Committee is to identify and address issues and problems concerning all aspects of the continuing education of our society members. The Education Committee is also concerned with the involvement of the students in the society, as well as the geotechnical education at the Canadian universities. We thank to the Canadian Geotechnical Society for supporting this series. So as usual, we start with a safety moment. And today's our safety moment is stretching at the workstation. As we all are spending a lot of time in front of the computers, so working at a computer involves very few changes in body position. This lack of movement can lead to muscle pain and strain as well. So no matter how well a workstation is designed, we need to pay attention to how we work. So some quick suggestions: take a micro break, stand up and/or stretch for each hour spent at a workstation. You can see some quick stretching tips on the right side figures. Vary the work task. I mean, break up keyboarding task work by doing other job duties or tasks that involve moving around or changing your body position. Try to stand up and move around on a regular basis, and relax your muscles, stretch and change position as you see fit. So before we get started, I want to say a thank you to our sponsor, Northern Crescent Incorporation, who is the sole sponsor of this webinar series. So Northern Crescent is a multidisciplinary engineering firm serving all phases of project delivery. Their journey began in 2010 with a focused vision to provide engineering services to a wide range of our clients. Having built a solid reputation, their industrial base has now broadened to include multidisciplinary engineering, including geotechnical engineering support for oil and gas facilities, chemical plants, fertilizer plants, industrial and residential buildings. They have a strong R&D team who are collaborating with several universities on very interesting geotechnical projects. Thank you, Northern Crescent, for your generous offer. A few housekeeping items. So we are on YouTube till to date. There are 159 subscribers with almost 2K views for our 2 videos that we uploaded. So if you haven't checked those out, please check those out. Again, as I said, this event is being recorded and the recording will be uploaded to our YouTube channel. A PDF copy of the presentation slides will be made available to the attendees upon request. So if you need the presentation slides, please reach out to us. We can send you a copy of that. If you have any questions regarding the lecture, there will be a short moderated question answer session after the talk. So please type your questions into the chat box and we'll make sure that Bruno and myself will try to answer those questions. Being said, we are so lucky to have an excellent speaker for our this webinar today. So Bruno starts is a visiting professor of offshore geotechnics at Ghent University. He's also a scientific researcher, offshore wind infrastructure lab. Since 2006, Bruno has been working as a geotechnical consultant to the offshore oil and gas and renewable energy industry. He has worked on projects worldwide, including several joint industry research projects to improve geotechnical design practices. As a visiting professor, Bruno is responsible for the offshore foundation course and supports the other geotechnical courses in the curriculum. His research interests include monopile soil structure interaction, the influence of geotechnical properties of backfill on cable soil interaction, and the application of data-driven methods to geotechnical design. Bruno is the author of the open source geotechnical Python package Groundhog, aiming to bring high quality geotechnical functionality to geotechnical engineering education. This package is used extensively in the courses at Ghent University, and I believe today we'll get the opportunity to know more about it. With that, Bruno, the stage is yours.
Thanks so much, Shama. Just going to share my screen to start the presentation. So if you could just let me know when that becomes visible, then I can kick off and go ahead.
I can see it now, Bruno.
Perfect, thanks. And thanks once again to the Canadian Geotechnical Society Education Committee for hosting this webinar series. I think this is very much appreciated by the entire community. I'm very happy to contribute with this talk today on geotechnical engineering automation. I will talk about my experiences in automating geotechnical calculations and try to give you some examples of what went well, but also discuss what didn't go so well in the past. I have a bit of feedback. Is that possible? Let me just... Okay, that's fine. Okay, feedback is gone. Right, so let's start off with a short introduction. So as Shama already mentioned, I've been working in the offshore industry. So my background is mainly offshore geotechnics. Been doing that since 2006. And I think two of my project highlights include the first wind farm design in Germany. That was very interesting and challenging. And since then, the offshore wind industry has obviously taken off. And I think another highlight is the ultra deep waters for the Colombo oil and gas project, where I designed suction pile foundations. These oil and gas fields in more than 2,000 meter waters depths, they pose particular challenges to engineers. I spend my time at two universities, so I teach courses at Ghent and I'm a researcher at OILAB. OILAB is a consortium between University of Ghent, University of Brussels and the Belgian offshore wind industry. And I think, well, offshore wind has sparked a lot of R&D lately and also data-driven design, as I will talk about later in this presentation. My interests revolve around everything that is related with data and how we can make informed decisions based on the data we get, and also be aware of the uncertainty that data carries within itself. So reliability-based design in geotechnics, I don't think we often do enough of that to communicate what the uncertainty on our soil properties means in terms of the uncertainty on the outcome. Offshore, especially where data is generally sparse, the quantitative integration between geophysics and geotechnics is an area which should deserve more attention and which I think will develop in the coming years. And then finally, I also like to do some numerical analysis and especially develop geotechnical software to make our day-to-day life easier. I think this slide very much captures the evolution of offshore projects and what it means in terms of geotechnical data. Because when I started in my career, there was only oil and gas work. And for oil and gas, we designed a single platform or a limited amount of structures for an offshore field development. And we had relatively extensive budgets for site investigation and subsequent foundation design. But offshore wind has turned all of that a little bit upside down, because in offshore wind, the costs that are related to site investigation go up as you have more locations to investigate. But at the same time, you need to produce designs at many more locations. So that has been the driver for design automation and going from site-specific data to site-specific design at 50 or more wind turbine locations. And my involvement in the offshore wind industry has really shown me the value of geotechnical automation. In this presentation, I'll first of all talk about why we can automate geotechnical calculations and how we can do that in a well thought out manner. And I'll also discuss some of the caveats and pitfalls for automation, because even though there's a lot of promise in automation, it is not without its downsides if done improperly. I think in our careers, we'll have to keep on building skills, and I'll talk about what I think is important in terms of skill building for geotechnical engineers of the future, especially in terms of transferable skills, skills that can be used wider than within just the geotechnical domain. I think those things, the thinking about how to automate calculations and how to build transferable skills, were at the basis of the Groundhog Python package, which is now available open source. And I'll give an overview of what that package is capable of and how you can use it to learn more about Python and automation and generally get more value out of geotechnical data. And I'll finish off with two examples that you will also be able to run interactively yourself. If you have a working internet browser, that's all you need. And these examples will cover Cpt processing and a basic example from axial pile design. So, geotechnical engineering automation. I think the reasons why we automate are fairly clear. Yesterday, I was quickly, because this is a webinar for the Canadian Geotechnical Society, I was going through the Canadian Foundation Engineering Manual. And if you look at that manual, it's a very extensive document with lots and lots of formulae and correlations, which are sometimes specific for certain sites, for certain pile types, etc. So if we look at that and we look at that worldwide, we can definitely acknowledge that geotechnical engineering is a semi-empirical discipline where we have many correlations, many calibrated design formulae, and sometimes even site-specific calibrations or site-specific information that enters into the mix. If we can have proper implementations of those formulae, that will help us a lot. Geotechnical design, in addition to that, is often codified in codes and standards, the API standards, the ISO standards, Eurocodes, etc. And we can follow basically well-defined cookbooks or codified recipes to implement our calculations. So that codification is asking for proper implementations which are reusable. We live in an age where computing power is not a limiting factor anymore. So if we look at conventional geotechnical designs, it's very easy to repeat a design 100, 1,000 times in a matter of minutes, as long as the calculations are not too complex and there's not finite element analysis involved, for instance, we can do everything quickly and run sensitivity studies. But even if we look beyond the conventional calculations, if we look at advanced tools like finite element programs or GIS software, we can take advantage of automation to script up these tools and to generate analysis quickly. The advantages of automation, I think, are fairly clear for anybody who's ever done an implementation of a method. Once you've done it properly, you obtain results faster and you will be able to run your calculation many times. The implementation is done once, that's a hurdle to pass, but once it's done, you will have less errors further along the line than when you have to go through the calculation manually time and time again. Also, if you start automating from very fine-grained functionality, for instance, the formulae for unit skin friction along a pile shaft, you can incorporate these automated formulae into a bigger algorithm, an algorithm that integrates unit shaft friction to obtain the shaft friction of a piled foundation. So if you automate properly, you can increase the complexity of your workflow significantly while maintaining confidence in the results. And I've already mentioned the importance of sensitivity studies. When we know what parameter variations mean in terms of the impact on our final result, we will be able to either make informed decisions on the foundation dimension or order additional site investigation. Automation is not without its problems, and I think I can say that I've automated certain things successfully, but I've also struggled a lot with automating fairly complex analyses, or have been stuck with bugs which I've scratched my head on for days until they were finally resolved. And I think this cartoon by XKCD captures everything we need to know about automation. We might start off very ambitiously with a target to reduce our time consumption on a problem, and finally end up with a code that we keep on maintaining and keep pouring time into because it simply does not cover all of the use cases. So when we set out to automate things, we need to do that with some clear strategies in mind. And often those strategies will also require some retraining on behalf of engineers. If we look at the skill set of engineers, programming is usually in that skill set to a lesser extent than the conventional skill sets of a geotechnical engineer. So that retraining is often a hurdle that we have to overcome. The other thing which I've seen also both in teaching and in practice is that when you automate tools, you can end up with creating black boxes where people just plug in numbers but completely have no idea of what's going on the inside. That is clearly not the objective, because we want to make life easier with automation, but we also want to provide more insights to engineers as to what is happening inside of the automated calculation. And finally, we need to acknowledge that we are humans and we're not perfect. So any automation that we do may carry errors inside of them, and being prepared to solve those errors during the lifetime of a tool is much better than thinking that we have solved everything from the get-go. So doing automation also requires the full backing of an organization. That can be a university where students are being taught the principles of a programming language like Python from the undergraduate courses and can then carry out over those skills into their further studies. Or it can be at the level of a company where conscious decisions are made in which path to follow towards automation. I think things are best illustrated with an example. So everybody knows the formula for drain bearing capacity of shallow foundations. It's well known, and you think, okay, this is a formula, I'm just going to get to work with that, implement that in the software, and then I'll be able to carry out hundreds of bearing capacity calculations. Well, that's technically true, but in reality, things are not as easy as they look. Because once you dive into these formula, you will often see that there's specific choices that are involved. I think one of the things we can highlight here is if we look at the bearing capacity factor in gamma, we have different choices. We have the formulae by Vesic and Meyerhoff, or we can have the rough and smooth formulae from Davis and Booker, but we need to decide which N gamma factor we're going to implement, or are we going to keep that parametric and allow the user to choose between these methods. Also, if you look at this graph from the book by Muni Budu, you can see that he stops presenting the results for friction angles of 40 degrees. If we implement this calculation, do we allow friction angles of 40 degrees? Or if people specify them, do we round them off? These are all questions to ask, and you cannot do automation without making those decisions. I think what is also a common mistake is a mistake on units. Do we put everything in kilonewton per meter cubed, for instance, for unit weights, or is it newtons per meter cubed? Do we use SI units or imperial units? This might seem like a far-fetched question, but certain industries still use imperial units. And also, are we satisfied to just have the bearing pressure as an output from this calculation, or do we want more? Do we also want the intermediate outputs? And how do we go about generating those intermediate outputs? So there needs to be some thinking before we start automating. And we have to balance those two seemingly contradictory aspects, where on the one hand, we desire speed, accuracy, and ease of use, but on the other hand, we want to keep things transparent. we want to make our functions reusable, and we also want to make sure that all our functionality is tested. So on the one hand, we want to go fast, but we cannot go fast before going slow, first of all. In order to automate, we need to build up skills. And I like to talk about transferable skills as skills which are not connected to a certain software or certain method, but are used throughout an entire career of a professional. And if we can make a wish list of what we want the geotechnical engineer of the future to do, I think we can all agree that we want our geotechnical engineers of the future to have a solid understanding of soil mechanics. I think that comes first, and people need to be able to reason from soil mechanics principles to solve foundation-related problems. Also, when site investigation is gathered, the geotechnical engineer needs to be able to translate that data to input for geotechnical calculations and then carry out those calculations. I think those first 3 bullet points are things that you would find in any job description of geotechnical engineers today. And these are also the skills that the currently practicing geotechnical engineers are most likely or should are desired to have. But with the advent of increased digitization, we also need to make sure that we look beyond the conventional skill set and try to build some skills which are perhaps not specific to geotechnical engineering, but will help us a lot will help the geotechnical engineer a lot in developing his further career. And the first one is data literacy. If we can work with data, process large volumes of data, access databases, clean data, filter data, then that has its uses in further automation efforts. Also, calculation methods change, and even though codes change slowly, engineers still need to be able to make updates or prepare workflows which suit their specific design situations. So some development knowledge is also desired. And then finally, geotechnical engineering is an experience-based discipline. We can all agree on that, I think. But it would be nice to also be able to quantify some of that experience into models, and to an extent that is already happening with correlations. But also, if engineers possess large data sets, for instance, from installation records, if they can apply machine learning methods, then that would be very nice, a very nice skill to have and to develop. Job adverts are always wish lists, and we always have to settle for what we get rather than what we want. And we can consciously ask ourselves the question whether we are not asking for too much from our engineers, because the skill sets that we're describing require a lot of training, a lot of development, and I think it's fairly impossible for engineers to have all of that knowledge from the get-go. But I think we do have to acknowledge that there are multiple uses for engineering profiles. Perhaps not everybody will have an appetite to automate things themselves, but if they can have a supportive role in an organization, a university, a company, which actively does automation but uses other skills, people with more qualitative experience in that process, then we can put different profiles to very good uses. But if we have people that are interested in automation, it pays off to invest in their digital skill building and allowing time for them to learn about scripting and programming, and to do that in a proper way, because later on in the process that is going to pay off. If we look at other business sectors, for instance, mainly commercial sectors, we can see that digitization has often permeated those sectors a bit more than engineering. If we look at ERP systems, CRM systems, which are heavily automated with artificial intelligence in the background, then we can perhaps say that engineering is lagging a little bit behind. And I think several organizations still need to start on their digitization journey. But I think everybody needs to start somewhere, and acknowledging that automation can yield benefits for your organization is the first step in that process. We are also not starting from scratch, because even though geotechnical automation may not have had the same focused effort as other industries, we can build on the experience that was developed within those industries. And one of the trends that we can see is that Python has really emerged over the past couple of years as the scripting and programming language of choice in technical professions. And learning Python, I think, is definitely a good skill to have. Software development has introduced further good practices that we can use within geotechnics. For instance, source code management using the Git tool is going to be very efficient. If you have a code base and you put it under source control with Git, you can see who made what changes. You can roll back changes, merge your code base with new changes, and all of that sort of comes with a relatively easy interface. And once you start using that, you wonder how you ever got by without. The principles of continuous integration are another aspect which I think is very transferable to engineering, because in continuous integration, what we will do is we will set up a series of tests on our code. This can be hand calcs that we check for geotechnical calculations, or results from literature that we check against. And every time we release the code base, we will run those tests in an automated way. And so any new release of the software will pass a number of tests. And that assures us of code quality. Python in specific has very good functionality as well to generate documentation from code in an automated manner. So today we can't really think of code without thinking about its documentation, and knowing what the code does, I think, is sometimes even more important than being able to use it, because when you know what it does, the using of the code will follow automatically. In numerical and scientific computing, we also don't need to start from scratch. We don't need to implement or optimization algorithms or differentiation algorithms. Those are all available to us in NumPy and SciPy. And I can say that Python packages have reached the same level of scientific computation possibilities as more advanced commercial packages like MATLAB. And then finally, the other Python library that I would like to highlight is Pandas. Pandas is a tool for data manipulation, and once you start using it, you wonder how you ever did things in Excel, and it just becomes that much easier and automated if you start using Pandas. When people talk about transferable skills, they usually talk about intangible skills, so things like problem solving, analytical thinking, things which stay quite vague. But I think that engineers can develop a series of tangible skills which are transferable, so even if they decide to move on from geotechnics to other disciplines, that they can carry over those skills and still have useful knowledge for their future careers. I think data literacy and scripting in particular are examples of those tangible transferable skills which will aid the engineer in his entire later career. And we all have to face that we will have to keep on learning, have to keep on studying during our entire career. So selecting those skills and those courses which will build up your tangible transferable skill set is recommended, in my opinion. Just another example of how transferable skills affect what people do in their careers. Just read up on these two scenarios. The first scenario is of a person who has been working in a company for 10 years. He's a software developer. He's been working on closed source tools, and then he's been working on a code base which has largely been static since its development. And then you're faced with the decision, should I hire that person? The other CV that you have is from somebody who has been working self-employed. They've been using open source tools, and even though things may not be so close to your area of expertise, these people have demonstrated the ability to learn new things, to treat new information in an agile manner, and to also share their knowledge freely. So I'm not going to make a judgment on who you should hire here. I think that's up to everybody individually. Both profiles obviously carry their merits, but if you want to invest in the skill set of the future, you should think about which profile would be the best choice for your organization. I've mentioned Python a couple of times, and again, like any choice we make, Python is a choice, and there are other languages out there which can do data processing like R, or we can do things in MATLAB. So why have I chosen Python? Well, the first reason is that it has a large community. Any programmer will know that when you're stuck or have a problem, you can go onto Stack Overflow and find answers to just about any problem that you may be facing. In addition to that, there is a rich ecosystem of packages which extend the basic functionality of Python, and you can do anything from scientific computation to data manipulation. I've done web development with the Django package, created advanced charts using Plotly or Matplotlib, and machine learning has become very accessible with the scikit-learn and Keras packages, or pytorch if you prefer to use that for deep learning. The other thing is that in addition to scripting and creating workflows yourselves, there is also often a scripting interface to advanced software. And both Plaxis, Abacus, and Itasca numerical analysis programs nowadays have Python interfaces which allow us to script up those finite element simulations and basically run simulations in batch and do sensitivity studies on numerical models like we would do them on conventional models. And then on the data visualization side, GIS softwares also have the ability to plug in Python procedures to do analysis or to visualize data. So I think as a Swiss Army knife of programming languages, Python is a good choice for engineers to focus on. And we also see that in undergraduate courses, increasingly there is adoption of Python precisely because of all of the opportunities it offers later on. This might be a difficult point for many engineers. I know engineers tend to use Excel. People have been using Excel a lot. People are also often very proud of the spreadsheets that they've developed, but why should I ditch my trusted Excel spreadsheet and invest all of this time into a new tool? Well, there are disadvantages to using Excel, and I think the first disadvantage is to acknowledge that Excel workflows, when you get a spreadsheet from somebody else, that these workflows are hard to trace. You can move down a column, you can move left to right on rows, or you can move in the third dimension through worksheets. And then you even have the so-called evil fourth dimension of VBA, Visual Basic for Applications, which can make Excel spreadsheets a nightmare to figure out. And with Python, the workflow is often a lot more linear. I will show you examples of some linear workflows with Jupyter notebooks. And those workflows are easy to follow, and you can see what's happening, and you have nice documentation statements in between. The other disadvantage of Excel is that once you've written a spreadsheet and the spreadsheet gives you a solution, it can be quite hard to reuse that spreadsheet in another workflow. Often this can involve manual copying and pasting of results. And then, what do you do if you have to repeat that 100 times? Do you just take the hit? Or do you still decide to look at VBA to automate things? It's in the scaling up of workflows that Excel is often facing difficulties. And then when you generate your analyses, often one workbook will correspond to one analysis case. So your automation possibilities are limited, at least if you want to keep your spreadsheets clear and easy to read. The Excel formulae, personally, well, I don't really like how Excel formulae are written. I don't really like to read that my cell is equal to A2 plus B6 to the power 2 minus C3. I don't really know what that means in physical terms. And I think that's where functions in a proper programming language are much more transparently encoded and much more readable, and will allow you a better insight into what's going on. And to finish off with the advantages of Python, even if you have old spreadsheets, there are Python libraries out there which will allow you to quickly read those spreadsheets, to read the inputs from them. And in the examples, I will also show how you can quickly read Excel input. Because for manually entering inputs, Excel still has its merits, and also for sharing data, you can still use Excel formats, but you should make a conscious choice when Excel is a tool of choice. So with all that being said, the question which was in my mind is, can we build a community-driven geotechnical software package, acknowledging that many of our engineers will never code things themselves, so they will still, can we prepare something that allows them to use code rather than to have to write it themselves? And can we somehow make that transparent enough and intuitive enough so that it gets adopted on a reasonable scale? In that, we need to acknowledge that people want, engineers especially, want to have a bit of freedom. You want to organize how your workflow goes, and you want to be able to make your choices, do site-specific correlations. If you want to exchange one relative density correlation for another, you should be able to use that. If you want to change a certain calibration parameter, these are all freedoms that should be provided. And in the development of such a package, what we can't ignore is that software development best practices exist. So we want to make sure that our package is properly tested, that it's extensively documented, and that it also operates according to the single responsibility principle. And the single responsibility principle means that one chunk of code is responsible for one specific action, so that you don't have repetitive sections of code which all do the same kind of thing. That reasoning gave birth to Groundhog, and the Groundhog put its head above the earth for the first time late last year. And now the package has been on GitHub for a couple of months. And in this section of the presentation, I'll quickly guide you through what Groundhog is, why it was created, we've already discussed that to some extent, and how it can be used. And the structure of Groundhog functions is something which is fairly unique to the package, and which I will demonstrate with an example. So Groundhog is developed as a sort of a framework in which we can plug in any geotechnical functionality. I started off with sol profiles, CPTs, some axial pile design, but in the future, I want to keep on developing this package to have more and more functionality as we keep on adding to it. The implementations need to be robust, and also we want to be able to transparently show what the insides of the calculations do. So at this URL, you can access the Groundhog documentation, and I will show you a little bit on how you can read that documentation and see what is required to use Groundhog. Anybody who wants to contribute to Groundhog can. It's a fully open sourced project. And on GitHub, you can flag issues that you have with the code. You can contribute your own code or just simply follow the development of this code. The code was released under Creative Commons license, a non-commercial share-alike license. So that means that if you use Groundhog, you can do it freely for studying purposes, and you have to attribute the authors and also share your work that you do based on Groundhog under the same license terms as Groundhog itself. The package has now already been used extensively in the courses at Ghent University to process CPTs, to do axial pile calculations, and also in the research that we do at the University of Brussels and the University of Ghent within OELab. We make extensive use of that package and are able to do automated analyses much quicker and with much more confidence than we would have done before. So Groundhog was created to be reliable, first of all. Reliable and transparent, because we wanted to give people insight into what was happening inside of the code, And one thing to do that is to simply look at the implementation of the code itself. You can always look at the source. But at the same time, we wanted to give people who don't have programming knowledge insight into the code as well through extensive documentation. And you can see an example here of just a simple phase relation equation where we calculate bulk unit weight from specific gravity, void ratio, and saturation of a material. So we describe, first of all, what the function does, and then we describe what the input parameters are. We want to have the saturation as a value between 0 and 1, so unitless, not in percent. We want to have a void ratio. We put some limits on that as well. Generally, these are physical limits. And then specific gravities can be optionally entered. The default is 2.65, and the unit weight of water is also optional. 10 kilonewton per meter cubed is the default value. Groundhog returns multiple outputs. So here we will both return the bulk unit weight and the effective unit weight from the material, and we return that as a Python dictionary. So Groundhog does not only return the end result, but also possible intermediate results. And finally, to finish off, we have a reference that you can consult if you have further questions or want to do further reading on a certain subject. Getting to use Groundhog is often the first step, which people sometimes find a bit hard to overcome. But if you use this link, that link will also be shared afterwards. You can simply run Jupyter notebooks in the browser, and you can get started with some Groundhog tutorials and simply follow those step by step. If you do want a local install, I recommend that you install Anaconda. Anaconda is a Python distribution which comes pre-packaged with a lot of useful packages, and then Groundhog is not packaged into Anaconda by default, so you need to install it using pip. So either in a bash shell or a command prompt, you simply type pip install Groundhog, and then Groundhog will be installed in your Python environment. Once you have Anaconda on your system, you can also open Jupyter notebooks on your system or create new Jupyter notebooks yourself. In the documentation of Groundhog, there is also some guidance for the installation. The basic structure of Groundhog functions is that Groundhog functions are always validated, always have documented units, and that they always return multiple outputs if that is required. So I've also already demonstrated that a bit for the unit weight calculation. The same applies here for the Jamilukovsky et al. Relative density correlation. And here, for instance, that correlation, the literature says that it's been calibrated to vertical effective stress conditions between 50 and 400 kPa. So we have validation limits imposed on that. Does that mean that we cannot extrapolate? No, I will show that later on, but that extrapolation will happen in an informed manner rather than implicitly. If we read up on this function, we can we can see which input parameters we need to plug into the function and which units they have. And we can also see that all of the coefficients of the equation have been made parametric. So if you want to recalibrate Jamilukovsky, if you would have a data set that allows you to do that, then this function is actually ready for it. You can recalibrate that formula and still use the Groundhog function by specifying these optional coefficients. The return from the function is both the dry and the saturated relative density, both as values between 0 and 1. And so Groundhog documents that extensively so that you know that you don't have relative densities in percentages. In code, importing that function is relatively straightforward. That function is part of the PCPT correlations module of Groundhog, and that module sits within the site investigation package, site investigation in situ test PCPT correlations, and then we can import that relative density correlation and we have it available. To use the correlation, we simply fill in the input values. So here we enter a QC cone tip resistance of 20 megapascal. a vertical effective stress of 100 kPa, corresponding to about 10 meters depth, and a coefficient of lateral earth pressure of 0.8. And if we execute that function, it returns a Python dictionary with a dry relative density of 72% or 0.72, and a saturated relative density of 0.83 or 83%. If we simply want to use the saturated value, we can access the dictionary element like you would in Python. If you don't know the Python syntax, if you take a basic course on Python online or elsewhere, you will be able to use Python dictionaries and simply have the numerical value available to you. What happens if we go outside validation ranges? That's a valid question, because when we write a loop with this map lambda statement, that's a Python statement to loop over multiple values of vertical effective stress between 10 and 500 kilopascals, well, then we see that when our vertical effective stresses are below 50 kilopascal or above 400 kilopascal, then a nan value, not a number, is returned. So, okay, but what happens if we want to know the relative density for a vertical effective stress of 20 kPa? Is that something that we can't do then? No, the answer is you can, but what you need to do is you need to specify an optional keyword argument in the function, and you have to say that your sigma v naught f, so your vertical effective stress, that the minimum value, so double underscore min, is equal to 10. And thereby you will explicitly extend the validation ranges of the function, and anybody who checks that function will be able to see that you have actually extrapolated very quickly. So by doing that, we can actually have relative density values, but we should be careful interpreting them because we go outside the calibrated bounds of the correlation. You will see that for certain functionality, Groundhog makes use of classes, and object-oriented programming is something which can be very useful, but sometimes for people starting out, quite difficult to understand. But it's best to think of a class as a representation of a geotechnical entity, like a CPT, or like an axial capacity calculation, or a soil profile. And that class has attributes, so things like the CPT data, the title of the CPT, the location of the CPT, and it also has methods, so operations that we can perform on the entity, like loading data, applying correlations, plotting data which are stored in the entity. If we use object-oriented programming and class-based definitions for our entities, we can rigorously apply that single responsibility principle that I've mentioned before, and we avoid having very long sequential code bases, but rather have very concise methods where we can actually really straightforwardly trace back what is happening where in the code base. Currently, Groundhog already has quite a bit of functionality. I'm hoping to still extend that in the future, hopefully with the help of the community as well. The first thing that is possible is soil profile definition and manipulation. Soil profiles, so layerings with their associated parameters or soil types, these can easily be manipulated in Python. The soil profile class does this. Cpt processing is another thing on which I've focused attention, because getting CPT data in and processing that efficiently helps people gain insight more rapidly. And especially during courses, I want students to be able to practice a lot. Shallow foundation design is encoded. The API ISO shallow foundation design procedures for VH, combined vertical horizontal loading, are in there. Axial pile design according to Belgian practice, the Beers method, Eurocode 7. But if you look at other standards, I've looked at the Canadian methods, so there's nothing really stopping us from also getting that into Groundhog at some point. Cyclic soil behavior is an area where we do focus a lot of attention within the offshore wind engineering research. And that's why I've also codified, or at least translated, many of the cyclic interaction diagrams for clays and sands into Python functions and graphical representations to be able to process cyclic test data rapidly. Community engagement is really essential. I've seen that both during the courses and during our research. If you have people using the code, then it gets better. Because even though they might bump into errors, we are going through an iterative workflow, a convergent workflow, which goes to ever better code. And remember that we are unit testing our code, so every test that has been performed in the past is re-executed every time that we release the package again. So we are really trying to converge towards a solid package for geotechnical engineering, where people can contribute code and also support the package development in many possible ways. Okay, enough about the principles behind Groundhog. I think it's time to talk about some examples. And the first one, because I think it's so basic for geotechnical engineers worldwide, is to show some CPT processing. Processing site investigation data is a very common task, but we are often faced with the difficulty that the site investigation data comes in many different files and formats, and we somehow need to be able to get that all into the same framework. Groundhog does that and takes CPT data from various sources and puts it into the same kind of workflow, the same kind of representation of cone tip resistance, leaf friction, and pore pressure, which is then carried forward into further processing. When I started off teaching, students were processing CPTs in Excel. So within one exercise session, we often didn't get much further than simply plotting the CPTs, let alone normalizing things or applying correlations. And what I really want students to do is to have exposure to many different CPTs, because geotechnics is an experience-based discipline, but the sooner you can start building your experience, the better. And I think students also already have an opportunity to start building up their experience. The second example is on axial pile design, where we have a fairly complex method to go from CPT resistance to pile end bearing resistance in Belgium, where the CPT is basically considered as a scaled down pile. And when we apply the method to go from cone tip resistance to unit end bearing, we correct for surface effects. The pile will feel the effects of the surface for a longer time than smaller diameter CPT. We need to correct for the fact that the CPT will feel stronger layers later than the pile. The pile has a larger diameter, smearing out its effect over a larger depth. And also, if there's a weaker layer below the pile tip, then that will be felt before it is felt by the CPT. Implementing that algorithm is way too complex for students to do within an exercise session or even within multiple exercise sessions, and that's also not the objective of teaching a geotechnical course. I'm not interested in whether students are good at implementing correlations. I'm interested in then developing an insight based on that methodology to see what things like increasing pile diameters does to pile capacity, and actually offer insight into into the implications of these methods and what lies at their basis. So without further ado, I will open up these Jupyter notebooks. After the webinar, you will be able to do that interactively in the browser yourself. In the browser, if you open up a Jupyter notebook, you will see that there's a tree-like structure and you can navigate to these notebooks, so the CPT processing tutorial to begin with. And here, what I want to do is to basically load some CPT data and process it. So going from the raw CPT data, applying the corrections for total cone resistance, normalizing cone resistances, and then applying some correlations, and at the same time visualizing the data in an easy manner. So this Jupyter notebook is an example of how linear workflows with Python work. We can execute these cells one by clicking on the run button or by typing Shift Enter. And if we do that in sequence, first of all, we will load the pCpt processing object from class from Groundhog. So pCpt processing allows us to create CPT entities and then add data to them and do further processing. We will also import the Pandas library for data processing. We will use that a couple of times in the workflow. If you don't know that, you might get familiar with Python, with Pandas syntax later on. The first step in the workflow is to load our data. First of all, we will create an entity for the CPT that will be loading. So this CPT is an offshore CPT from the Borsele wind farm area. This has been made publicly available under Creative Commons license by the Dutch government. And that's obviously very helpful to have open data, similar to Databank Ondergrond Vlaanderen or other open data initiatives to demonstrate CPT profiling. So we can create an entity for the CPT. Currently, there's nothing in it. So we need to use one of the load methods in Groundhog to add data to that CPT. And here we have our CPT data encoded into an AGS file. AGS files, I can show you the example, are a standard geotechnical data transfer format which allow you to transmit data in a fairly structured manner. So there's a convention in which here this, for instance, this SCPT underscore DPTH represents the depth of a CPT point, and this SCPT underscore res represents cone resistance in with their respective units. So it's quite hard to actually digitize that, and if you would have to start that from scratch, that's not a really nice task to do. But Groundhog has the load AGS function in it, and you can simply provide the path to this file and then say which keys are used to store the Z data, the Z key, the QC data, the FS key, and the U2 key. If you are unsure what to do, you can always look at the documentation, and you will see here in the documentation of Groundhog that this load AGS function takes the path, the Z key, the QC key, the FS key, etc. And you can enter these keys yourself in the code. So here our depth is SCPT underscore depth with the units between square brackets. And then we can load up that data. And we can also, for discontinuous CPTs, add a column for the push. So for discontinuous CPTs, we might have multiple pushes, and Groundhog is able to handle that as well. Plotting the raw data is very straightforward. We simply have this method called plot raw CPT, and we can customize some plotting ranges. But if we plot here, we can actually see that there's something wrong with our FS data and our U2 data. And the reason for that is that if I look at the file, my sleeve friction and my pore pressure were given in kilopascal rather than megapascal. And Groundhog expects us to have these in megapascals rather than kilopascal. So we need to identify the multiplier on FS. So we will multiply all our FS values by divided by 1000 to be in megapascal, and do the same for U2 for the pore pressure. And if we use the correct multipliers, you will see that the CPT appears as we would expect it to be. So you can see there's a couple of soil types within this profile. We have some sandy soil at the top, fairly hydrostatic pore pressures. And then we have this sort of interbedded layer, a sand layer, and then a clay layer. This pore pressure looks a bit off. Maybe there was something wrong with the sensor there. Well, that's something that you can examine quickly by visualizing things with this plot raw CPT function. And then you can always look at the data itself, because the data attribute contains the data, and the head function displays the first 5 rows. So this is the data, Z in meters, QC in MPa, FS and U2 also in MPa, and then a couple of other columns which got loaded because they were present in the AGS file. Then, when we want to correct our data, we need to specify what the cone properties are. And Groundhog expects those cone properties in a default format. So we need to specify the area ratio, especially. That's an important one. And if we look at the area ratio, so we can load that with our AGS converter. If you want to read up on that, Groundhog can convert AGS files in an automated manner. We can see that our area ratio here is 0.58. And I've pre-prepared an Excel file with these cone properties. So from 0 to 30 meters, we're using the same cone with an area ratio of 0.58, and it's a piezo cone with this base area and this sleeve area. We can load those properties and then have those cone properties available. The same for layering. We want to create a layering because Groundhog will base its further processing on those layerings. And I've also encoded that layering in Excel manually with the total unit weight, which is required, and the soil type, which is also required. And that layering is then simply read from Excel and is now available in the Python workflow. What we then want to do is we want to map that layering and those cone properties to our CPT. So for each CPT data point, we want to say, look, CPT data point, you're in this layer, and you have this cone property that is being used. And that's what the mapping does. And if the CPT has lots of data, sometimes this mapping can take a little bit more time. It's a function which I also welcome anybody with some computer science interest to optimize a little bit. But usually, well, it remains acceptable. Once the properties are mapped, we can look at the data attribute again. So if we look at cpt.data.head, we will see now that we have added quite a few columns. So for each data point, the area ratio, and then also vertical effective and vertical total stress calculation. Based on that, we have everything we need to conduct the normalization of the CPT, and that is done with the normalized CPT function. If you look at the documentation, the normalized CPT, if I look it up, the normalized CPT function will basically carry out the normalization and apply all of these formula in one very straightforward one very straightforward statement. So we can do that and then see that even more columns are being added to our data frame, but we don't care because these columns are simply stored in memory and we don't need to worry about them that much. We only, when we need them, we can use them. And that's the nice thing about Python. You don't need to worry about your spreadsheets exploding or anything. It's very easy to add data to your classes. And then we can plot the normalized data as well. So plot normalized CPT, plots the normalized quantities, and this shows that the initial layering selection was not that bad. Perhaps you might consider moving these layer boundaries a little bit up or down, depending on what you see here. Exporting data to Excel is also straightforward. So once you've done the mapping and you have all your data, you can export it to Excel. So you simply say CPT to Excel and then the output path, and that outputs the data to an Excel file. And this is an example, and you then have the data of the CPT, and then the layering you used and the cone properties that were used as well. Soil type classification with a Robertson chart. If you have to do that manually, it's a tedious task, but Groundhog is actually plotting the Robertson charts and the data per layer in one easy overlaid plot. And we can, for instance, look at the last layer, which is, which from the CPT data looks like a cohesive layer, and then the layer above is sand. Well, the Robertson chart really indicates that these brown data points are definitely in the region 3, which is cohesive material. And then layer 5 is purple, that's here within the 6 to 7. So that is definitely cohesionless, sandy material. And that allows us to also not only determine the soil type, but also see how much scatter and how much uncertainty we have on those CPT-based soil type classifications. Applying correlations of soil parameters is something which we often do because the CPT is a cheap and fairly straightforward test to execute, and lab testing takes much more time and is much more expensive. And Groundhog has a number of correlations implemented. If you want to know which ones, you can import this dictionary and you can see the location, the correlations which are currently available. Also, all those correlations are also documented in this pCPT functions documentation module. So for each of the correlations, you can check what the formula is, which units are required, etc. Here in the example, we will calculate relative density and undrained shear strength according to the formulae by Jamilkovsky for sand relative density and the SU for red and lun. For the sand clay layer, we need to make a distinction. Or decision. Do we want to treat that as cohesive or cohesionless? Then it's always good to look back at our data and to actually see that in this interbedded sand clay layer, we seem to have excess pore pressures. So based on that information, I decided to treat it as a cohesive layer. Applying a correlation in Groundhog is straightforward. We just need to find out what the name is of the correlation. Here it's Dr. Jamilkovsky et al. We need to specify which column we want to create. So here we want to create a column Dr and then unitless. And then we want to specify to this apply correlation method what output from the Jamilkovsky function we want to use. So here we are in a submerged state. So we want to use the saturated relative density output. And that will get mapped to that column. And as an other argument that is needed, we need to add the K0 coefficient. So here we simply add K0 of 0.8 throughout. We apply this only for sand. So here we specify a Python list, which includes the soil types for which we want to apply it, because obviously applying a relative density correlation in clays is not really something which is very, well, that doesn't make any sense, basically. And then if you run that correlation, you will get warnings, but that's because of our validation ranges. Here it says that your sigma V0 F cannot be smaller than 50 kPa. That's how the correlation was implemented. If we want to go beyond 50 kPa and extrapolate, we can simply say that a sigma V0 F min is, for instance, 10. But then we are extrapolating, and we should be conscious that anything above 5 meters might be less reliable. So now we will see less warnings. And then get the relative density that way. We can check the data and a column dr will be added to it. But initially, if the data is too shallow, that will contain none values. I can also set the validation range to 0, but that's maybe not the best thing to do because the relative densities that we will then get are negative. So that is very meaningless, and that's because the CPT has not developed its full resistance yet. So here I will keep it at 10 for now. You can also see how easy it is to make changes in these workflows by simply typing additional arguments and varying things. The undrained shear strength correlation is applied in the same way. So we are going to store SU in kPa as the result of this rad and lun correlation. And we need to specify the NK factor. For North Sea soils, we generally know that NK is between 50 and 20, but we need to make that decision based on lab testing normally. Here we're going to apply that correlation to clay and sand clay, as I've mentioned before, and applying that correlation is done in just one simple code execution. Finally, we want to visualize the results of our correlations, and we can do that with a log of the soil next to the plots. And first of all, we need to say which colors we want to attach to which soil types. So sand is yellow here, clay is brown, sand clay is orange. And then we will create a plot with 3 panels, one for QC, one for the relative density, and one for SU. We won't show legends, and we will show QC between 0 and 100. Relative density between 0 and 1.2, and SU between 0 and 500. And the stick marks can also be customized, and the titles as well. Notice the latex. Maybe if you're familiar with latex, you'll probably love it, like I do. If you're not familiar, you can just type plain text as well. And then executing that code cell in one go generates your plot with your QC trace, your soil profile, and then also your results from the relative density calculations. So no results in the clays and in the interbedded sand clay, and your SU calculations where you only have results in the clays and interbedded sand clays. And then just as a little bit of a cherry on the cake, you can starting with an individual CPT is the basics, but you can easily automate things with Python over multiple locations. So here we can do that, creating multiple Groundhog CPT objects and loading data in each one of them and assign, well, we can expect, for instance, first CPT here to see what it looks like. And then we can assign coordinates to each of these CPTs, because once we have coordinates and elevations attached to CPTs, we can draw profile lines and visualize those CPTs along a profile. That is done with the plot longitudinal profile function in Groundhog. And if we want to, if we execute that function, we can see all those 4 CPTs along a profile line, starting at WFS1, ending at WFS6. And for the intermediate CPTs, we can see which offsets they have from the profile line. So that is all calculated in Groundhog, and you can infer what spatial variability you have. For instance, here you can see that this cohesive layer, you can trace it between the boreholes and it seems to be getting thicker. And then this competent sand layer seems to dip down as you go more towards WFS 1, 2. So these are the basics of some CPT processing with Groundhog. And I invite you to have a go and simply run the notebook in the browser whenever you get the chance. I think I'll soon finish off, but the Beer and bearing method workbook works in a similar manner. It's a bit shorter now than the CPT notebook, but we can create a De Beer calculation, so a calculation which transforms QC into unit end bearing QB, and do that from a CPT. So we load the CPT again, and now we load the data from Excel. We can see that this data is now, this is from an onshore CPT. Often in Belgium, it's still with a mechanical cone, so you won't have the resolution from an electrical cone. And often also sleeve friction information or pore pressure information is missing, but that doesn't stop us from applying de Beers algorithm. De Beers algorithm is a fairly complex algorithm, and the paper itself is more than 50 pages long, so quite a hefty thing to read. But the algorithm is, you can implement that without problems and compare it to previous implementations. And the advantage of Python is that users have insight into what is happening inside of that formula. So the first correction that you will do is the correction for the surface, presence of the surface, which is felt longer for the pile. Then you can correct for the stress level, because the stress level, the stress induces by the pile is higher than that of the CPT. Then you can do a downward correction, accounting for the fact that the pile will feel stronger layers before the CPT feels them, and then an upward correction accounting for the fact that the pile will feel weaker layers before the CPT feels them. And all we need to do is we need to pass the depth information and the QC information to that De Beer calculation, as well as the pile diameter. There are a couple of quirks in the De Beer method, and I think that will be the case for any national method. For instance, De Beer requires resampling to 0.20 meters. That is because it was developed based on a mechanical cone. So we can't forget to redo that. But with this workflow, we can also show to students what the importance is of that resampling. That if we apply De Beer on an electrical cone, that we will end up with completely different results. We will specify a layering here based on the preliminary CPT information and set those soil layers for the De Beer calculation. We can check what that layering is, and the effective stress calculation is also performed, and those stresses are required for the base method. Running the algorithm is all isolated within this method. So if you execute that method, the calculation happens, and you can see that it happens very fast. We can check the detailed calculation results here. So if you want to dive deeply into that algorithm, you can. And then finally, what is more instructive is to actually plot the base resistance. And here you can see the averaging that has happened on the CPT trace. So at about 10.8 meters depth, we have the maximum unit end bearing of 4.08 kPa. If we would increase the pile diameter, which is really easy, so increase it to 0.8, we simply re-execute everything. And we end up with more averaging because the pile is carrying its load over a larger area, and therefore also less unit end bearing. Okay, that was it. So to conclude, I think it's safe to say that automation is not going to go away. We can't simply shove it under the rug and forget about it. I think a lot of the adoption of automation will come from fostering an innovative and open mindset, and to look for opportunities that these tools can give us. Be eager to learn from other disciplines, to look beyond the boundaries of geotechnics as well, and to invest in developing lifelong transferable skills. The balance between automation and insight, I think that is very important, and writing good code takes time. So doing something quickly and dirty in terms of automation is going to cost you later on during the process. Providing documentation, I think, is indispensable for engineers if you want the code to be used and the code to be transparent. And also for students, that critical thinking where they actually go back to the documentation and investigate what is going on is something that I want to develop. So as a closing remark, I invite you all to check out Groundhog, to try out its functionality, to check the interactive tutorials, and to see if you can apply it for your courses or problems. Thanks very much.
Thank you very much, Bruno. I think this is a wonderful presentation. So we are a little bit over time, but still a lot of audience are with us. So that means it's definitely a great presentation. So thank you for that one.